electric field between them. We'll place that into a magnetic field. We're going to stick a little screen here, with a little hole right in the middle. All we have to do is add one more thing from what we had yesterday. Let's put a magnetic field over on this side of the screen. And it could be the same field as this, or it could be a different field, depending on how you want to design this. So it doesn't have to be the same field. And let's see if you can recognize what we just made. So what we're going to do is take some sort of charged particle. We're going to fire it in here. And we're going to adjust the electric field and the magnetic field so it goes straight through. But once it gets to our screen and passes through the little hole, it's no longer in the electric field. So now what's our little particle going to do? Here's what would have happened if it kept going straight. So what does your right hand say our particle's going to do? So what's happening to it right here? Going up, right? But if we make this little chamber back here big enough, what path is it actually going to take? So initially right here it goes up. So what's it going to actually do? Start to curl. In fact, if we design this right, we can get this to come around and hit the back side here, where this then is the radius of that path. So let's see what all that did for us and see at what point you recognize what this is. Because some of you do know about this, by the way. Let's see. We know this. We know how fast that particle is going right here. All we do is, we have to do is adjust the electric field, magnetic field, until we get our particle to go straight through. Whatever the ratio of these two is going to tell us the speed that we're going through there. We can pick different speeds that we want just by adjusting these fields. And we know the radius of that path, so we took a look at this the other day. So what useful information could this give us? And we'll take a look at it in a more simplistic term. I'll tell you here in a second what they really look at. So we know where this thing hit. You have a little screen there, you can actually see little particles hit. Actually, you saw that with this oscilloscope. We had a way where they were fluorescing the screen so you could see where the little particles were hitting. So we can figure out where they hit, which means we know the radius of the path in here. We know how fast those particles were going because we sent them through a velocity selector. We can know what the magnetic field is here because we can adjust that to whatever we would like. So we know this. And here's the one little assumption I'll make to simplify this a little bit. Let's say we knew the charge of this particle when we sent it in there. Anyone know what this device is yet? So let me back up a step. What this device can tell you about this thing that you fire in there?
It tells you about its mass, right?
Tells you the mass. Those who've had chemistry, you know what that is? How many of you have heard of a mass spectrometer or a mass spec? There's a very basic mass spec. What mass specs actually really do is they give you the mass charge ratio. But from that, you can actually tease out the mass. We'll look at it in a simple case where if I do that charge, all I need to do is fire this in there and know what my fields are. I just have to see where this thing hits the screen. And based on the radius of that path, I can figure out the mass of the particles that are going in there. So if I send a bunch of particles in there of different masses, they're all gonna have the same speed right here, because I send them through a velocity selector. So I know what the speed is, and if they're different masses, they'll just hit different spots on the screen. And from where they hit, we can figure the mass out. So kind of a slick way to get masses of charged particles. Any questions on that? Let's see, how about this one? So we'll take a top view of this one. What we'll do is make a device with a couple pieces here with a gap in between. And these are going to be some conductors. And what we're going to do is connect these two, and here's a new symbol for you, to an alternating current source. All that means is we can send the current one way or the other way. So we can design this so that we can send current one direction or the other direction. So send a DC current in there. We'll have the option of doing that. We're going to put little thing right here. And what that little thing will do is create some ions. So that's going to be a little ion source. So maybe it makes, for example, some protons or something like that. So it'll create some ions. Then we'll set this in a magnetic field. So we'll drop this whole thing into a magnetic field. And just for some orientation, let's make this one out. So here's what we'll do. This thing will make a little, say, proton. So here's our little proton. And at this point, what we'll do is send a current into our device with a little alternating current thing so that this side is positive and this side is negative. If I do that, that means there's a potential difference between these two. So if you want to think electric field, there's an electric field that way, or there's a potential difference between here and here. What does our little positively charged particle do if I let go of it at this point? This is positive, this is negative, or if my electric field in this gap is that way, what's my little positive charge do if I let go of it? It heads that way. Wasn't moving at all, and now it moves this way. At this point, when it enters in here, so here's where your potential difference is. Here's where that electric field is, just from here to here. So once it enters here, it's not in that electric field anymore. So now what does our particle do? We've got a moving charged particle that's positive, it's moving that way, and it's in a magnetic field pointing out at the board. So now what does it do? So what kind of path does it take? Initially it gets deflected down, but what does that do pathwise? Curls around like this, right? And what's going to determine the radius of that path? These things. It's not moving very fast though. So kind of a small radius. So it comes around like this. And here's the one trick to this device. At this point, we're going to flip the direction of the current that we sent in there. And now this side's going to be positive, this side's going to be negative. I'm going to end up with an electric field that way, in that gap. So when our little particle pops out, if we switch our current right there, now what is he? Flies this way. In fact, when I say fly, is it the same speed all the way across? Nope, we've seen that. It's going to go faster, faster, faster. Which means when it hits here, now it's out of the electric field, so it's going to curl, but which way? Up, right? And how is the radius going to compare to this first one? It's bigger because it's going faster. So a little bit bigger radius. Then we switch the direction of the current again. And we go like this. You want to recognize what this is yet? What's happening to our little particle the whole time? Every time it crosses this gap. How come I'm drawing these circles bigger? Yep. And faster and faster and faster. You know what that is? We have a particle, and what's our particle doing? How do you say in physics words faster and faster and faster?
So this is
Oh, our particle is what? What is this thing?
It's a very rudimentary particle accelerator.
It's a very early particle accelerator. And that's how you can get particles up to speeds like you see in those homework problems, 2 times 10 to the 6 meters per second or something like that. This was actually the first design of the early particle accelerator. This was actually done back in the 1920s when they came up with this. In fact, if you want to add this in, here's how you can accelerate these things. Put a velocity selector on the back end, and you can get just really fast but single velocity particles out of it, again with an additional velocity selector. Although this is pretty simple, these are still used in nuclear physics, particle physics. They're actually used in medicine. So how would that have a medical application? So this is used for things like creating ion beams that you can hit cancer cells with. So you get high energy, which means fast moving ions. This is a way you can do that and end up trying to treat cancer cells with those. I was going to see if I had some other stats here. There's one of these I read about in Canada that, well, I couldn't find a picture of it or anything, but what I read was that it's used for particle physics, nuclear physics, and medical uses. And the magnet that they used just for the magnetic field part was an 18-meter diameter. So imagine the whole device is pretty big. This original one was a little handheld version, but you could still get particles moving up near the speed of light just with this simple concept. So just a couple interesting devices based on some of the simple things we've talked about so far. What happens if you look at moving charges in magnetic fields, and we saw that there can be a magnetic force on those. But what happens if instead we constrain our moving charges inside a wire? So let's say here's a wire, and let's put that in a magnetic field. Let's say a magnetic field is going into the board. We've got a wire laid right on the board, and let's send a current this way through that wire. Well, hey, that's moving charged particles in a magnetic field, so there should be a force on those particles, but they're constrained in that wire, so what we're actually going to end up seeing is that there's a force. It's really on the charged particles, but it's going to look like there's a force on that wire. what's going to be the direction of force on the wire in this case? Which way is that wire going to get pushed? Into the board, out of the board, to the right, to the left, up, down? What's the direction of the charged particles? Remember, current is in the direction positive charged particles are moving if they were the ones carrying the current. So that's up, right? So thumb up. Fingers which way? Into the board. So which way is this guy going to get pushed? So this would put a force on that wire this way. If I flip the direction of the current, I get a force the other way. If my current was down, fingers into the board, it would actually push the wire that way. Well, we've got forces on wires. It would be a lot more convenient if we could have an equation that would let us look at forces on wires based on the current running through them, rather than the one that we did before. So here's what we had before. We had a magnetic force that was this strong, and we had a right-hand rule to figure out the direction of it. But this is the magnitude of it, where we needed to know, hey, how much charge did we have, how fast were our charges going, how strong was the magnetic field our charge was flying through. Well, that does apply to this, but it's not that convenient, because here I know other things. I know how long my wire is, I know what kind of current I have going through there. So let's see if we can take this same equation and recast it into something more convenient for us to look at forces on current carrying wires. So let's do this. So current is a flow rate of charge. It's flowing charges. So a way you can say that mathematically, it's the amount of charge you have going by in a certain time. That's a math way of saying flow rate of charge. Or, let's rearrange that. The amount of charge that we have is just the current that you have flowing times the time that you're going to count that. That's your grand total charge you've got due to some current. Let's see. We know from first semester physics that velocity is a distance over time. Well, let's make that distance some length of wire that our current's going through that's sitting in the magnetic field. So that's a length of wire over the time it's going to take for that current to flow through that, or for our charges, I should say, to flow through that chunk of wire. In other words, let's rearrange that. No, we don't have to rearrange that one. Let's put these things into our equation over here. So our magnetic force is charge. Well, let's put it in this way. So there's our charge. Let's see, let's do this. Yeah, let me redo this. Let's do it this way. Do it in 2 steps. This might make more sense. Let's swap out time for length over velocity. So again, velocity is distance over time, so time is distance over velocity. So that's this guy. Notice these guys disappear. And what we're left with then, it's the same equation, it's just cast a little bit more conveniently for forces on current carrying wires, because now all we need to know is how much current do we have going through our wire? What's the length of our wire that's in the magnetic field? How strong is the magnetic field? And then what's the orientation between the direction our current's going and the direction that magnetic field's pointing? So again, it's the same thing as this one. It's just more convenient for current carrying wires. This is the thing we're gonna play with a little bit later today. That's what all this stuff is sitting on your table for. We'll actually explore that and take a look at how that actually works. So I mentioned that to this day, by convention, we consider the direction of current, the direction positive charges would be moving if they were the ones that were actually doing the moving in the wires. And it does make it easy for right-hand rules and things like that. If I've got a current going up, I can think of it as positive charges going that way. But what really is doing the moving in those wires? What are the charges moving?
Negative charges.
Yeah. Specifically, what negative charges?
Electrons.
They're electrons. They're the ones really moving. Show you how they actually figured that out. That it was negative charges, not positive charges. It's actually a fairly simple setup. So let's take a conducting strip. Like this. A strip of copper or something like that that's conducting. Let's send a current through there. And we're going to send a current to the right. So the question is, if my current is to the right, is it positive charges going that way to the right or negative charges going that way to the left? Who's doing the moving? Positive charges that way or negative charges that way? Let's do this to figure it out. Let's place this strip in a magnetic field. And start watching what's happening. Let's send our first little, let's assume it's positive charges, so that means to the right. Let's send our first little positive charge in there. So here it comes in there. Once that positive charge enters the magnetic field, what's it going to do? So we're going to keep it moving that way, but what's it going to do? There's a magnetic force on it up, so it ends up here. Put him right here as he scoots across. By the way, that means there's a net negative charge down here, which means we've got just a slight electric field built up in our little strip. So now let's send a second one through. It again gets deflected up by that magnetic force, and we send another one, and another one, and another one. But as we continue to send current in there, continue to send charges in there, what's happening to the electric field across our strip as we send more and more charges through? We're getting more and more positives here, more and more negatives here, so what's happening to our electric field?
Potential difference.
Our electric field's getting stronger, 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 right? Eventually, what's going to happen to our little positive particles as they're going through? Hopefully that picture's starting to look familiar, like something we've already done.
Well, eventually they're going to build up positive charges up top. It's going to start to repel the protons.
So right now we had this to start with. But we're building up this. Eventually, so initially we had just that. As we build up our electric field, this is getting bigger, 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 bigger. Eventually, these match. So what do our particles do from then on? Going straight through. So we've reached a steady state, our particles are going straight through to the right. We're okay there. Okay, what if instead, same setup, it's negative particles going to the left? Which way is that going to deflect? So remember, negative particle, you have to flip your thumb opposite of the way it's going. So it's moving that way, so I'd start like that, but oops, it's a negative particle, I have to flip my thumb against the direction it's going. Fingers into the board, so which way is it getting deflected? Up. So sort of the same kind of thing where, whoops, it ends up here. That means there's a net negative or positive down there. I just start to build a little electric field. I get more and more and more. If I take a look here, I've got my magnetic force up. What's the direction of the force, the electric force on that negatively charged particle when it's sitting here? It's down. This is negative, this is positive. So there's a, sure enough, just like before, you get that. Eventually, those two forces are equal, and once those get to be equal, then all my charges are going right straight through, and we've reached a steady state, and I've got this nice flow of charges going through. How do I tell the difference between those two? Was it positive charges that way or negative charges that way? How do I distinguish between those two cases? Now that now that we've reached that steady state and I've got my current flowing.
Can we try inverting the magnetic field and see what happens?
No, that would just flip these. It's easy, and you guys have all done it. Of how to distinguish the difference between those two.
Reverse the currents.
You guys did it with the, oh, even easier. You guys did it with the vinegar batteries. How'd you figure out what was the positive terminal? And you back up a step from there. One of the very, very first things we did is I had you take a battery, one of these guys, and figure out how these work and how to measure the voltage of this. And you took the little pokey things, and you did this, right? And it measured the potential difference between those two, right? What happened if you went backwards?
You get negative.
You get a negative answer, don't you? All you have to do go like that. See what you get. Which is positive, which is negative. If the top is positive, it's this case. If the top is negative, it's this case. Simple as that. And sure enough, it ended up, it was this case. But that's how you could actually figure out who's doing the flowing. Is that making some sense? Think about it. If not, let me know. Let's see, one more of these kinds of things, and this is just going to get us just the first start. We'll have to add some more things to go beyond this. But let's say I've got a loop like this that's conducting, so I can send a current through there. And let's do this. Let me draw some things so we can see this. So let's say I've got a current going this way around the loop. So it's going around like that. And let's place this in a magnetic field. I'll use this, I guess, as my pointer. So it's immersed in a magnetic field that's pointing that direction. So I'll just show one of the field lines, but there's field lines all through here. So I've got a magnetic field this way, and a current going like that. Is there any magnetic force on the top of this loop?
Wait, I'm sorry, could you repeat that?
Is there any magnetic force on the top of the loop?
When the current is flowing in the direction
Yep.
of the arrow?
Yep. what's the angle between the direction the current is flowing and the direction of my magnetic field line? They point the same way, right? There is no angle between them, it's zero. What is the sine of zero?
Zero.
Zero. How about down here on the bottom? Now my current's going that way, my magnetic field is this way.
Doesn't really matter, it's still zero.
Still zero. That's a 180-degree difference between
It's
those
like
two? Sine of
zero
that is
versus
zero.
negative
So
zero.
no force here, no force here, right? What's the direction of the force on this part of the loop? So current's going down, field's that way. What does your right hand say? Remember, these are right hand rules.
It's gonna be, the force is gonna be pointing outward.
That way, right? So no force here, no force here, I've got a force there on this side. What's the direction of the force on this side? Now my current's that way. Current's up, field's to the right. I've got force this way. What's this loop going to start to do? I won't say completely do, but start to do. That.
Start to spin.
I'm going to start to rotate it. If we stop right with what I said, it's not going to keep rotating. We'll see that later. But I'm going to get it started at least. We're going to come back to that and see how are we going to make this thing spin. But hopefully you see I can get it started at least by putting a loop in a magnetic field and sending a current around that loop. I can get at least the start. Because this side's getting a kick out towards you, this side's getting a kick back towards me. And at least doing that to it. So we'll finish that off a little bit later when we add some more stuff, but I'm going to just start there. So I'm going to switch gears a little bit and get at, all right, so what really is causing things to be magnetic in the first place? I'm going to show you one of the great accidental discoveries. It's amazing how much of great science is done accidentally. Part of this is having an awareness to recognize something just happened. So this one came on July 21st, 1820 by a guy named Oersted. And if y'all come up here, I've got this set up so you can see this. And while you're up here, I did track down one of these from the back room where all the geology stuff is. This is a piece of magnetite, so it's just a rock. But you can see that rock is magnetic. So this is the stuff that people were studying since ancient times, and the Chinese figured out how to use this to turn other things into magnets. So I did find a piece here that's actually magnetic. So here's what Oersted did. He was in like a big lecture hall doing these lectures, and you know, about this time of the semester, rooms get like they are here, where there's junk laying all over the place. So he had stuff laying all over the place, and he was doing some demos of electricity, you know, 1820, so way back in the day. And he just happened to have stuff lined up just right for this accidental discovery. So he was just looking at some things with currents going through wires. So I've got a little setup here. Thought I'd show you kind of an old school rheostat. So this does the same thing those blue things do. So there's a blue one back here. It's an adjustable resistor. And if you look at how this is set up, what I'm going to do is send current into here. And that sends it into these little coils. But notice I didn't connect here, because this is how it would have gotten out. It went all the way through the coils. It's even trying to get out here. I'm not going to let it, because I'm not going to connect there. So the only way to complete this circuit, the only way for that current to go, is through however number of loops I decide, and then up to this thing, and then across here and out. And I can slide this back and forth to pick how much resistance I want. The further I am that way, the more of this resistor I pick up. So I did adjust this earlier today, but I want to see how that worked. So what I'm going to do is send a current through here, and here's what Orsted had fortuitously done. Is he happened to have a compass underneath his wire. And he happened to have them lined up just right. So I may need a little help if I need some people to hold this in place. And so he turned his current on. You all see the compass there? And, whoa, compass needle reflected. What does that mean? What did the current just produce? A magnetic field. So that was how they actually discovered that. Oh, look at that, currents produce magnetic fields. Within 2 weeks, Ampere had sorted all this out with some experiments. And one of the things he found, so I need a bunch of hands here. So I need this held this way. One of the things he found is what the direction of that field was. I'm going to switch compasses here. This one's a little bit more sensitive. It's tiny, so hopefully you can see this. So you guys all see, get in. So right now, nothing's going on, so of course our compass needle is pointing that way towards me, or geographic north, I should say. Well, what I'm going to do is turn the current on. That's going to make a magnetic field in the wire, and we'll see if we can map out what that field looks like with this little compass. So, and notice, by the way, which way that current's going through that red wire right now. So it's coming out of here through there, so it's going that way. Okay. Turn this on and check compass. Looks like it's going that way. But right here, oops. I've got a magnetic field that way. They go on this side, and the magnetic field's that way. Picking it up a little bit. And if I go on that side, it's that way. So how do I say that? What's the field actually look like around here? It's looping around like this right now. And I mentioned this the other day, there's a nice simple right-hand rule to figure that out. I've got a current going that way. I probably know which way that magnetic field is wrapping around created by that current. I grab the wire with my right hand, I thumb in the direction of the current, with my moving charge particles, and here's my magnetic field wrapping around like this. If I switch the direction of the current, and wait for me to do that, I'm just going to switch these two rows. So now my current is coming out like this, now it's going down. And so you can check it out. Oops. So turn on current and check. Oop, on this side now it's that way. And on this side, oops, it's that way. This side, that way. Inside to that way, so notice it's now wrapping around like that. Again, got a nice easy right hand rule. I turn this that way, grab it with my right hand, there's no magnetic field on. So, thanks. Appreciate that.
So when are we going to get to shoot ball bearings through these rheostats?
You're not.
Would that even work?
So let's say here's your wire. And again, we're not trying to do three-dimensional things. So wires like lined up like this, and we're going to send actually a current, we do this way, out of the board, sorry. That's going to make a magnetic field. So out of the board, right hand, fingers curl like this. That makes a magnetic field, if I were to draw a field line like this. And what do you suppose is happening to the magnetic field as we get further and further away? What do you suppose happens to the strength of the field? gets less and less, so a way I could draw that is with my spacing of my field lines. So here's another one, next one's further out. So this would be sketching that magnetic field. So again, Ampere, within a short period of time, had figured that out, and he even figured mathematically, or to figure out quantitatively, how strong is that field around a current carrying wire. It was this constant, and that's on your little cover sheet. Certainly, the stronger the current, the stronger the magnetic field's going to be, but the further away you are, the weaker the field is. And that field's got these little circular shapes. And so, sure enough, here's the little circumference of a circle. Again, the further out you are, the weaker that's going to be. So here's how strong that current's going to be. And again, we've got a nice, easy right-hand rule to figure out the direction. In that case, what should happen if I've got this set up? If I've got two wires, and I put them next to each other, and what happens if I send current through both of them, and the current's in the same direction? All right, see if you can follow this. Let's call this wire 1 and wire 2. So, wire 1, when a current runs through it, a magnetic field is set up around that wire, right? On the right side of wire 1, the plane of the board, what's the direction of the magnetic field created by this current? So grab it with your right hand, thumb that way. What are your fingers doing on this side? Poking into the board, right? So this is the magnetic field over on this side set up by wire 1. Well, look at this. We've got a current carrying wire in a magnetic field. That means there's going to be a magnetic force on it. What's the direction of the force on wire 2 because it's sitting in the magnetic field that wire 1 made? So, current's up, field's which way? In, what's the direction of the force? That way. So this will have a force on it this way. Okay? Now let's look at this. Wire 2 has a current flowing through it. That means a magnetic field is being set up around wire 2. Over on this side of wire 2, what's the direction of the magnetic field? So I grab it with my right hand. On this side, which way your fingers point? Out of the board. So wire 2 made a magnetic field like this on this side of it. Oh, look at this. Wire 1 has a current running through it. And wire 1 is sitting in the magnetic field that wire 2 made. What's the direction of the force on wire 1 due to the fact it's sitting in the magnetic field that wire 2 made? This way. So what do these two wires do if I turn those currents on? They come together. If I switch the current of one of them to the other direction, what do you suppose the wires do? They'll go apart. I'll let you walk through to convince yourself that actually happens. I did find a little video here. It's not the most exciting, and it doesn't really have sound. but thought I'd show you this. Something MIT put together that shows this. They're going to use some terminology. Oops, where they're going to say the current is in series or parallel. When they say in series, they're going to connect these wires up to a battery. In series meant the wire, or the current is going like this. So when you see that, that means opposite directions. In parallel, they meant current's going like that. So you'll actually see this stuff happen. Pops up. While that's popping up, let me do this real quick. An important shape is a current carrying wire that does this. It makes a loop. If I send a current, say this way around that loop, what's the magnetic field like inside the loop? So I want to look right here, right in the middle of the loop. What's the field like if my current runs that way?
It would be curling upward.
So all I want to know is right here. Nothing there. Grab it with your right hand. So, remember I said put pencils down? Don't worry, I see that all the time. And notice if I grab it with my right hand, my fingers pull up through the loop, so that makes a magnetic field this way through the loop. If I switch the direction of my current, where now my current's running that way, I can make a magnetic field going down inside the loop. What happens if I'll draw it and then kind of show it. Take my loop, instead of a single loop, make a whole bunch of them and stack them on top of each other. Take this guy and make a bunch of little loops like this and stack them. So it'd be like that. I'm just going to show a single one because it's a little easier to see. If I send the current that way, we get a magnetic field like this. If I do another loop, another loop, another loop, I still get a magnetic field like that. And it'll keep going up until it pops out. So I get a magnetic field that looks like this. Let's just start with 3 of them. And then down here, we go like this. In fact, notice I've got a north pole I've just made here, a south pole I've just made here. I've got field lines coming out of here, going into here. So this has a couple terms. These loops like that, here's the fancy term, is that's a solenoid. Does that magnetic field look familiar? Something else we've seen? We've seen that kind of a shape before. Looks like that. Almost looks like a bar magnet. Huge difference. This is got a fixed magnetic field. That one depends on the current I send through it. In fact, what do I do if I want to turn my magnetic field off?
Turn off the current.
Shut my current off. What if I want a stronger field? Turn my current off. That field's going to be related to how much current I send through there. Basically, what we just made is an electromagnet. And the advantage of electromagnets is you can control that magnetic field. I can turn it off, turn it on, make it stronger, make it weaker, just by the current that I send through there. All right, here's that quick little demo where they show the 2 wires. Again, there's no real sound to this. It's only about half a minute. All you hear is that like hiss, and I hear them like click the thing. So what they're going to do with the switch is let you either put the current opposite directions or same direction. So there's opposite direction, there's same direction. So you can actually see those forces acting on those wires. So series, that actually made opposite direction, parallel, they're going the same direction. So there's just kind of a visual thing, what we were just talking about. Okay, so with that, let's spend the rest of today taking a look at the force on a current carrying wire, or that magnetic force on a current carrying wire. Let me get you set up for it. And then if you need to take a break or anything, do that at your leisure.